Hey, hey, hey. So today we're going to try to keep going with notes. So the next section of notes, we're going to look at solving and modeling things with exponential and log functions. We kind of already looked at this before break, solving equations where we took the log on both sides and things like that. The only difference with the ones we're going to look at today is they're a little bit more complex. They might involve a few more steps. And then tomorrow we're going to look at some ones involving word problems, everyone's favorite. So let's get started with this. And then once you finish up with this, you'll have the rest of class to work on some practice questions again. So some things that are nice when we're solving with logs is that we can switch back and forth between log form and exponential form. The properties of both apply in those situations. A nice thing about exponential functions and log functions is they are one-to-one. So remember, that means that each input has a unique output. And that helps us out because as long as we have the same log on both sides or the same base on both sides, then we can figure out some things that are also going to be equivalent. So in this box here, they're one-to-one properties. If you're looking at an exponential function, and like I said, if your base is the same, then really those exponents have to be equal. So in this case, we have b to the u is equal to b to the v. Since we are told those are equal, what that must mean is that u has to equal v. Okay, so if those two expressions are equal and their bases are equal, then their exponents have to be equal in order for that to be true. Similarly, with log functions, if it's the same log base and they're equivalent, then the numbers inside also have to be equal. So again, u is equal to v. So really just like we did before where we were trying to get things to match up with bases and things like that, we're going to be doing the same thing to try to solve these questions. So let's go through and hopefully you'll see more what I mean with these next couple. So in question number 1, we want to solve that 20 times 1/2 to the x over 3 is equal to 5. So we're really trying to solve for that x and that exponent. And this one we can actually solve without using logs at all, solely by using algebra and what we know about exponential equations. So what I kind of want to do is I want to get rid of this 20 out in front, so that way I've got two things on each side. So I'm going to divide both sides by 20, which on this side gives me 1/2 to the x over 3. And on my other side, in order for this to be easier to see, I suppose that's the best way to put it, you want to keep this as a fraction. Putting this in decimal form is not going to help you solve it, so please be careful. 5 over 20 does reduce down to 1/4. Okay, so now we've got a fraction on each side. One side has an exponent, the other one doesn't, and that's okay. Our end goal here is to get it to look like that very first part of those one-to-one properties box where we've got the same base on both sides and just our exponents. So in this case, I can rewrite that 1/4 as 1/2 raised to some exponent. And that's going to give me the same base of 1/2 on each side, and then I can work with my exponents alone. So if I keep this 1/2 to the x over 3, I can rewrite 1/4, like I said, as 1/2 raised to some exponent. 1/4 is really 1/2 squared. So the reason we want to do that is now my bases are the same and we know they're equivalent. So what that means is I don't have to work with that base anymore. That base essentially becomes irrelevant. And what we know is if those are equal and my bases are equal, then my exponents have to be equal. So that x over 3 has to equal that exponent of 2. Now, this is a nice equation to solve. All you have to do is multiply both sides by 3 to get x by itself, and we get that x is equal to 6. Okay, so that's kind of what we're going to be looking at, are solving ones that are a little bit more complex like that. However, for the sake of things being too complex to teach you guys while I'm not in front of you, we're going to skip question number 2. Don't worry about it. It doesn't really come up a ton. It's a good one to look at, but it involves exponential equations and the quadratic formula, and it's just not worth getting into. So we're going to skip ahead onto the next page and look at two more ones involving logs this time instead of exponentials. So when we're solving log equations algebraically, we have to be careful with them and just keep track of your domain, just like we have with any other function. Now, generally speaking, when we looked at log functions before. I'll kind of sketch it off to the side. Remember, a normal log function looks like this. That's really bad, but you kind of get the point. If you want to graph a log function so you can see it a little bit better, go for it. But really my domain with log functions is from 0 to infinity, and it doesn't hit 0. We have that vertical asymptote there. And that is with a regular log function. If you're looking at log of whatever base of x, that's going to be what your graph is kind of going to resemble. But what I want to look at is something like number 3, because that becomes a little bit more complicated and we have to be a little bit more careful. Your graph, if you were to graph this, is going to look different because we have that x squared. And I want us to be careful when we're solving things algebraically for that exact same reason. So right here, I've got that we want to solve log of x squared equals 2. So what we're going to do with that is really talk about how we can rewrite things. Remember, this is really log base 10. So right now I really have log base 10 of x squared is equal to 2. And hopefully you remember from when we were trying to rewrite things in exponential form before. I'll kind of write this off to the side here. One of the rules that we looked at is that when we had log base 10 of 10 raised to some exponent, so say we had 10 to the third, then this really just simplified down to whatever your exponent was. Okay, remember that's what we were trying to get our bases and our numbers to match up. So that way our answer was just our exponent. So if I were to try to use the 2 that we have in this situation, what this would really be, subbing in 2 for y, is log of 10 squared is equal to 2. Okay, so I just switched out that y for a 2. Again, sorry for that handwriting, it's not wonderful. Now I'm going to sub that out on the right-hand side of the equation that I have in number 3. So I have log of x squared, you don't need to write that base 10, I was just trying to remind you guys that's what it was, is equal to log of 10 squared. Okay, so just substituting what we had. Now going back to those one-to-one properties that we talked about at the beginning of these notes, if you have the same log base and they're equal, then the things inside your logs are equal. So x squared is equal to 10 squared. That's nice because again, now we don't have to work with those logs. I can simplify this relatively quickly to get my answer. So 10 squared is 100. So I have x squared equals 100. And when I take the square root of that, I will get my values of x. Now I did say values plural because we have to be careful when we put the square root on things. Remember, we do plus or minus. The square root of 100 is 10. So here I actually have that x is either equal to positive 10 or negative 10. Okay, so just be careful when you've got exponents, it can sometimes change things. All right, and the very last question I want to look at today is question number 4. We want to solve this problem here involving natural logs. There's things on both sides. This looks kind of gross. Actually, the way we're going to solve this isn't going to be too terrible. We're actually going to solve this one graphically. The quickest way and easiest way to solve this graphically is to get 0 on the other side. So that way you only have to graph one function and then you're just looking at where it crosses your x-axis. So in order to do that here, I'm going to subtract that 2 natural log of x from both sides, which gives me my entire equation as the natural log of 3x minus 2 plus the natural log of x minus 1 minus 2 times the natural log of x is equal to 0. Now we could try to solve that algebraically. I'm not going to make you do that. It's pretty complex and we don't need to do that. So like I said, the way we're going to do this is to graph it. So I would just graph that entire function on that left-hand side. And then again, we're seeing where it's equal to 0. The reason that's nice is you can just find where it intersects your x-axis. If you were to graph this, you would see that this intersects my x-axis at x equals 2. So that will be our solution there. Now we're going to leave it at that as far as notes today. You have the remainder of class to work on the homework assignment that follows this. So the solving and modeling exponential and log equations homework. Today you could do questions 1 through 9 and 12 through 14. So go ahead and skip 10 and 11. Please be careful. The only questions in which it tells you you can solve it graphically are 13 and 14. So in order to receive credit, make sure all the others are solved algebraically. You should have extra class time tomorrow, so if you do not finish all of those questions, I know it's a bunch, that's okay. Work on it tomorrow in class. Please do not stress about going home and working on this. Again, I will answer any questions when I return. If you have any questions, though, in the meantime that you would like me to answer, feel free to email me. And we'll do one more video notes tomorrow, and then you guys should be done having to listen to me through a speaker. All right, have a great day. If you have any questions, again, let me know.